Hi, I'm Ori, and I would like to introduce our paper about verification under causal consistency. Let's start by considering a simple example. Suppose that we want to verify that the assertions in this program never fail. Namely, we need to check that the two writes to Z are in critical sections. And indeed, if the first thread runs first, then until it finishes its execution completely, the second thread will be stuck in the busy loop. Similarly, if the second thread runs first, then the first thread will be stuck in the busy loop. Thinking about it more generally, this verification problem is easily encoded as a reachability problem in one big transition system. Each thread is represented as a transition system, where the labels are memory accesses. The memory itself is also a transition system, whose states correspond to the different states of the memory. Then, we can check for reachability for each of the bad states in the system representing the intersection of the interleaving of the two threads and the memory. If the program has a finite data domain, as we assume here, then we get a finite transition system, and reachability is clearly decidable. Implicitly, we assume that our memory provides sequential consistency, where the different threads take turns communicating with one global memory. While this model is easy to understand, it is actually unrealistic. To improve performance, systems nowadays provide weaker guarantees, which makes this verification problem much more interesting. This includes many examples of multi-core systems, including hardware like x86, Power, ARM, and software models like C11 model. Concerning decidability of the verification problem, we know that verification under x86 TSO is decidable, and recently it was shown that the closely related release-acquire model of C11 actually leads to undecidable verification problem. Weaker models than sequential consistency naturally appear also in distributed storage systems, where there is a very large variety of models representing different positions on the CAP trade-off of consistency, availability, and partition tolerance. Our focus in this work is on causal models, which we refer to as causal consistency. Causal consistency is a classical and widely used consistency model. Intuitively, it allows nodes to disagree on order of writes to memory, as long as they all agree on the order of what is called causally related writes. This results in a model weaker than sequential consistency, in the sense that it allows more behaviors, and also weaker than x86, where the main difference is that causal consistency is non-multi-copy atomic. It allows different threads to observe different writes in different orders. Going back to the initial example, if we run this program under causal consistency, either in a multi-core system like Power, or you can think about each thread running in a different place in the world, communicating with a replicated data store, then we may get a safety violation. Since both writes initially are not causally related, both threads can read 0, and both will enter the critical section. This demonstrates the need in verification techniques for causal consistency. Before going on, I should say that there are multiple options on how to formally define causal consistency. The variant that we study in this work is called SRA. It is slightly stronger than RA, C11 and Java 9 release-acquire model. SRA precisely captures the guarantees provided by the Power architecture. If we compile C11 release-acquire programs, this means that Power doesn't actually exploit the whole freedom that C11 allows, but rather gives us SRA, which is slightly stronger than C11's RA. Finally, SRA is in fact the standard causal consistency model that is widely used and studied in distributed systems. The main contribution of our paper is this theorem. We show that the verification problem under SRA is decidable. What is also interesting is the new semantics that we developed for SRA that allows us to achieve this result. Before describing the new semantics, let me briefly define causal consistency more formally. The standard definition is declarative. It uses execution graphs. Let's see how it works in a simple example. In this example, we have flag-based synchronization. One thread is writing to Y and then sets a flag X to 1. The other thread reads the flag X and then reads Y. Under causal consistency, it is disallowed that the second thread will read 1 from X, but then 0 the initial value from Y. Let's see the reason for it. The first step is to draw an execution graph corresponding to the behavior in question. Here we have 6 events, 2 initialization events, and then 2 events for each thread representing the writes and the reads to the shared variables. The order on them is induced by the program, and it is called program order. Now we have to justify each read with the write event that the read reads its value from. Here we have only one option. The read of X can only read the value 1 from here, and the read of Y can only read the value 0 from here. We obtain the happens before relation. All paths formed by program order and reads from edges. Then causal consistency enforces 2 natural conditions. First, happens before should be irreflexive. It should not have loops, and this condition holds in our graph. Second, we should never allow this pattern. A read cannot read from some write if there is a write intermediate write in between them in the happens before order. We say in this case that the read is aware of the second write because of this happens before path, but the second write has overwritten the first one. This condition is violated in our graph. We have a read, which is aware of a write here via this path, but it reads from a write that is earlier than this write in happens before. So we say that this execution is inconsistent and the behavior as we wanted is disallowed. This is almost the whole model. What is missing is how to handle concurrent writes to the same variable. This is precisely where different causal consistency models go in different directions. I will skip most of the details here and just say that in SRA we have another existentially quantified order and we enforce certain conditions on it. These conditions are slightly stronger than the conditions of the array model, so we get a slightly stronger model. I don't go into details here because it has only limited significance. We showed in the paper that for programs without write-write races, namely without concurrent writes to the same variable, SRA and RA coincide. As a corollary, we obtain the decidability of verification under C11's RA model for programs that are write-write race free, and most useful programs satisfy this condition. Okay, back to the verification problem for the SRA model. Let me start from the bad news. We have a non-primitive recursive lower bound. This is simply because we can simulate lossy channel machines using causally consistent memory. This is the same bound that was previously obtained for verification under x86 TSO. Now for decidability, we would first want to make our semantics operational, so we can think about it as a transition system. This is easy. We simply say that the state of our memory, instead of being a mapping from variables to values, is an execution graph that represents the full history up to the current point. At every step, one event is added to the graph in a way that preserves the consistency using the conditions I presented before. For verification, we need to check that the graphs cannot evolve in a way that leads the program to an assertion violation. The problem here is that these graphs may grow unboundedly. Even when we have a finite state program, the program may still have loops. So the transition system that we get by synchronizing the program with a causally consistent memory is infinite state. This is what makes our verification problem so challenging. What comes to our rescue are well-structured transition systems. This is a general framework that allows us to establish the decidability of certain reachability problems in infinite state systems. To see how it works, let's see a standard backward reachability analysis. We start with some bad states, and at each step, we calculate the set of predecessors until we reach a fixed point. Then, we check whether some initial state is included in the fixed point and report if so. To make this work in an infinite system, we need to find a way to finally represent the set of states that we reach in each stage, and we also need to make sure that this process will converge. Well-structured transition systems achieve both of these. The idea is to have some well-quasi-order on the set of states, and then use upward closed sets to represent the set of states in the reachability analysis. The fact that we have a well-quasi-order ensures that we can always represent these sets with finitely many minimal elements. Then, for the reachability algorithm to be correct, we require that the transitions of the system and the quasi-order are compatible, which formally means that if we can take a step from a state Q1 to a state Q2, and we have a state Q1 prime that is larger than Q1, then there always exists a state Q2 prime that is larger than Q2, and Q1 prime can step to. When this condition holds, the analysis is both sound and precise. A standard way to achieve compatibility is to include an explicit lose step in the semantics. This allows the system to non-deterministically take a step from a state Q prime to a smaller state Q. Then we can always choose Q2 prime to be Q2. We call such systems lossy systems. Our goal is to find a faithful representation of causally consistent shared memory as a lossy transition system with respect to some well-quasi-order. If we take the states of our memory to be execution graphs ordered by partial order embedding, we have two critical problems. First, this is not a well-quasi-order. We can have infinitely many partial orders on a finite alphabet, and none of them is embedded in another. Second, it leads to the wrong semantics. If we simply lose a write event from the graph, threads may be able to read values that they couldn't read without losing the write. After thinking about this for some time, we encountered a psychological doubt. Why do I keep focusing on the past instead of the future? This led us to the key idea in the new semantics. Instead of maintaining the history of the execution in our memory state, we will record what we call thread's potential that tells us the possible future. The potential of each thread says what possible sequences of reads the thread may execute. Here is an example of how thread potentials work. Initially, the thread has in its potential the option to read 2 from X and then 2 from Y, and so on. Then it may actually read 2 from X and consume the first entry in the potential. After that, it reads 2 from Y. The lossy semantics allows the thread to non-deterministically lose some of the options in the potential in epsilon steps. So the thread can skip the X0 entry and finally read 0 from Y. The point is that losing options from the potential does not make the semantics too weak. It just means that the thread could read something, but didn't need to. The formal constructions of the semantics is given here. As states, we have functions assigning a potential to every thread, where a potential is a sequence of read options. Each of them is composed of a location and a value. Initially, we only allow the threads to read a value 0. Our well-quasi-ordered states will be a pointwise subsequence. A state Q is smaller than Q prime if for every thread, the potential of the thread in state Q is a subsequence of the potential of the thread in state Q prime. Here is how it works for our example. Initially, we started with the potentials that only allow to read 0. Then, the first thread writes 1 to X and adds a corresponding entry in the potential of the second thread. Then, the second thread can do the same and add the option to read 1 from Y in the potential of the first thread. Then, the first thread can read 0 from Y, consuming his option in the potential, and similarly, the second thread can read 0 from X. This leads us to the error state, where both threads are in the critical section at the same time. How do we maintain the potentials at each step? We have loose steps that allow us to remove arbitrary parts of the potential. Read steps can only be performed if the first element in the potential allows the read. And finally, write step first require that the writing thread does not have any read options to the same location in its potential, because after writing to variable X, I should not be able to read all values of X. And second, the write step should add entries in the potentials of the other threads. This allows them to read from the new write. The crucial question here is where we can add new entries. Before answering this question, know that this semantics is dual to the original semantics we had. Read steps are completely deterministic here. We cannot change our fate that is already ascribed in our potential. But write steps are non-deterministic. They set the potential. This is exactly the opposite to what we had before. Write steps just added events to the graph, and read steps were the ones actually picking the right event to read from. Okay, so going back to the question, where should we add new entries when a write is performed? Let's analyze two examples. In the first, we need to allow this behavior. After the first thread writes x1, the second thread should be able to read 1 from X and then 0 the initial value from Y. If we look at the potentials, then the option to read 0 from Y is in the potential of the second thread before the write of 1 to X by the first thread. So when the first thread does this write, it has to put the new option before an existing option in the potential of the second thread. On the other end, if we don't put any constraints on where to put the new option, we will break causal consistency. If we go back to the flag-based synchronization example, here we should not allow thread 1 to put the new entry before the existing entry to read 0 from Y. Because if we allow it, we would allow the behavior that first reads 1 from X, but then 0 from Y. These seem like conflicting requirements. Sometimes we need to allow to put a new write before existing options, and sometimes not. The question is whether the semantics gives us enough information to distinguish these two cases. And the answer is yes, and this is based on what we call the shared memory causality principle. It explains the meaning of causal consistency in terms of potentials. It says that every sequence of reads that thread pi can perform after reading from a certain write executed by thread tau could be performed by thread tau immediately after it executed its write. Intuitively it holds, since the view that thread pi will get after reading from thread tau must include at least the current view of thread tau. It means that if thread 1 wants to put a new option in the potential of thread 2, it has to be able to read itself whatever thread 2 can read after the new option. Then, to add a new option here in the potential, we will require that the suffix of the list after this option is a subsequence of the potential of the writing thread. Revisiting the examples from the previous slide, the difference is exactly in the potential of thread 1 at the point of writing 1 to x. In the first example, thread 1 can read itself 0 from y at this point, so it may input the new option before the existing one. In the second example, however, thread 1 cannot read y0 at this point. It has just written y equals 1. So it is disallowed in this case to put the new option before the existing one. These were the key ideas in our new semantics, and if you read the paper, you will see that there are more intricate details. We actually need to have more than one potentialist per thread. We need to carry the thread identifier of the writing thread in the read options, and we also need additional flags to handle R&W instructions. I did not mention R&Ws in this talk, but including them is essential. They are used in almost every useful example, and our results support them completely. Okay, so what we proved? First, we proved that the potential-based memory system is equivalent to SRA. We did it in Cork, and the scripts are available in the artifact. We then proved that the new semantics forms a well-structured transition system, so we can use it for decidability when it is linked with a program represented as a finite automaton. From that, we have the decidability of our verification problem under SRA. And as I mentioned before, for programs that are write race free, we obtain the decidability of verification under a slightly weaker array model of C11. Without this write race free DOM condition, this problem is undecidable for array. We have several directions for future work, starting from an implementation and including several more theoretical questions. We are also trying to use the potential-based semantics in other verification approaches, like program logics and abstract interpretation. Finally, speaking about potential, I'm looking for students and postdocs for my ERC-funded project. So if you're interested, drop me an email, and you may have the potential to regularly visit the wonderful beach in Tel Aviv. Thank you.